In this lecture, we'll discuss the rationale for database systems, and hopefully we'll dispel any image you might have of databases as mundane or dull. So, why study databases? Now, I'll confess that before learning more about databases, I was inclined to see them as glorified file management, the sort of thing that outdated, middle-aged IT types worried about, and certainly not a creative or technically interesting area of software. And for the record, I was wrong. In case you come to this subject with some of the same impressions, and I certainly understand if you do, let's spend a bit of time talking about why database management systems, DBMSs, are worthy of study. And the reasons fall roughly into three areas. First, ubiquity and importance. And second, technical challenge. And then third, employment value, which of course sort of derives from the ubiquity and importance thing. So, starting with that first up, let's look at how widespread and important databases are. Now, they usually operate behind the scenes, so it's easy to overlook them. But you can't use a website of any sophistication. You can't check out at a supermarket, make a phone call, or reserve a plane flight without tripping over a database. The automated grading systems for this class rely on one. The online systems you used to register for the class rely on one. The list goes on. So the world stops without databases. And the last half-decade or so have added a new dimension to this argument. The web has generated vast collections of information on customer behavior, web search patterns, healthcare, etc., all of it, of course, held in databases. An analysis of this information for hidden trends, which is often termed big data analysis in the popular media, is one of the most impactful new technologies of this decade, whether it's used for mundane purposes like improved product recommendations or life-saving purposes like finding better medications. Now, ubiquity and social value do not automatically translate into technical interest, of course. Clean running water is ubiquitous and important, but it's not high-tech. Databases, however, present all sorts of interesting technical challenges. You don't have to know all the internals to use a DBMS unless you're writing code for one of the companies that make them, but it's worth appreciating what's being done for you by the DBMS. Such systems as Oracle or MySQL, for instance, qualify as DBMSs. First up is a speed-size mismatch. Now, underlying much of the technical challenge in DBMS design is the huge difference in speed of access between large volume media, presently that's hard drives, and working storage, like RAM or cache memory. Now, newer solid-state drives ameliorate this to some degree, but they have their own problems, and they're not yet inexpensive enough to store large databases. Now, we tend to blur all apparently instantaneous operations together as too fast to see. It's kind of tempting to think, milliseconds, nanoseconds, whatever. Let's try a useful metaphor, a sort of thought experiment. A modern CPU can perform around 10 billion instructions per second. Now, if we slow time down by a factor of 10 billion, like some science fiction time-lapse story, and we look at the world in CPU time, we can get a gut sense of the difference between RAM, cache, and disk access times. In this CPU time, it takes 1 second to do an instruction. So the CPU is cranking away. Add this, store that, test this, at 1 instruction per second. Right? Now, accessing CPU cache, as of this writing at least, takes about 0.2 nanoseconds, a fifth of a billionth of a second. And main memory takes about 2 nanoseconds to access. So in the slowed down world of CPU time, that's 2 seconds for a cache access and 20 seconds to get a value from main memory. Be sure you follow that, because I'm going to ask you to do a little of it for yourself in an in-lecture question shortly here. Now, it's not unreasonable in this CPU world to have that amount of time to access those things, but you can see why we want CPU cache for speed. Even RAM access takes a while, 20 seconds, in this world. But disks with moving parts are in a class of their own. To get to any particular data requires moving a read head and waiting for the disk to come around to the right spot as it spins under the head. Now, this time varies per disk, but for your average PC, 12 milliseconds is a good estimate. And note, I said milliseconds, not microseconds even. And so we come to our first in-lecture question. This example is always more impressive if you do the math. So, in CPU time, how long is 12 milliseconds? Now, the correct answer should sound almost too large. Express it in units of months or years. Coming back from a pause, you should have paused and done the computation, followed through the reasoning I did earlier if you needed to. 12 milliseconds times 10 million, basically, is 120 million, 10 billion I should say, is 120 million seconds. That's 4 years. That's enough time for 120 million instructions in CPU time. Now this metaphorical 4-year access time influences everything in DBMS design. Even the way memory is organized on a disk is different than in RAM. You don't get a few bytes at a time from a disk. You get blocks of, say, maybe 8 kilobytes at a time. Now, if you're going to wait 12 milliseconds to get to the data, you may as well get a lot of it at once. And this, in turn, motivates all sorts of tricks to try to get data that is used in common into single blocks, to RAM cache commonly used blocks, and to organize collections of data that are larger than a block into patterns on disk that at least put blocks near one another to reduce that 12 millisecond access time. And we're not even considering searching the data. So let's do a few questions on that. Say I have a large customer database, 10 million customers, and 2 kilobytes of data per customer. So I'll put 4 customers per disk block of 8 kilobytes. Now if I search linearly through that list of customers, how many disk accesses will it take to go through all of them? And how much time? Don't even translate to CPU time. This one can be expressed in perceptible human time. Again, per usual, assuming you paused and came back from a pause, it's 2.5 million blocks given 4 customers per block. And if each takes 12 milliseconds, that's 30,000 seconds, or the better part of a day. Now, clearly a linear search is dumb. You wouldn't even do that in RAM. We'd surely keep those customers sorted in some way, and binary trees or a binary search is so much faster. Are they really? A balanced binary tree needs roughly how many levels to hunt through 10 million pieces of data, or equivalently a binary search needs how many different tests to search through 10 million pieces of data. And how long, assuming 1 disk seek per level or per test, would that take? And again, coming back from a pause of some duration there. Well, we're looking at a log to the base 2, right? So log to the base 2 of 10 million. That's about 23. So 23 seeks at 12 milliseconds each. And that'll take about 276 milliseconds. Okay, well, that's better. But a quarter of a second, which is what that is, of course, is still humanly perceptible time. And if I have to do that operation for perhaps 20,000 customers a day, the lookups alone are going to take 20,000 times 1/4, or 5,000 seconds, about an hour and a half. Any standard web server software would look up the relevant customer on every page hit during a web session, so the actual time would be perhaps much worse. So in the next segment, we'll finish up this list of technical challenges.